Okay, if I can have your attention, just like last time, I'm going to start with a couple of questions on the iClicker. So if you can get your iClicker going, and I'll try to do the same thing, meaning if we have time at the end, I'll go over the questions one more time, but that's not going to happen every time. Okay, so the first question is, let me send this to there. All right. Streamwise acceleration is the product of the rate of change of speed with distance along the streamline, and what else? Okay, I'm going to end it in 5, 4, 3, 2, 1, 0. Okay, let's take a quick look at your answers. Okay. Most popular answer is the pressure. Streamwise acceleration is the product of the rate of change speed with distance along the streamline, and what else? Okay, so if you answer pressure, think of the units. Right? You're looking for acceleration. Right? That would be, if you're completely lost, then you think, well, I'm looking for an acceleration. If I multiply the rate of change of velocity with distance, if I multiply it times pressure, do I get an acceleration? The answer is no. So that rules that one out. Maybe by the same token, we can probably rule out C, which is the second most popular. Because if you multiply viscosity times the rate of speed with, the rate of change of velocity with distance, which is velocity over distance, right? So velocity over distance will have units of meters per second divided by meter. So, which means 1 over second. So that rules out C. Density, same thing. So the correct answer is actually the one that only 26 people got right. As we look at the Bernoulli equation in a moment, we're going to show you that again. But let's go to another question. Here is just filling in the blank. An airfoil is designed so that the fluid velocity over its upper surface is blank that along its lower surface. Greater than, lower than, or same as. This should be a little easier. So let's go 5, 4, 3, 2, 1, 0. And this time, the majority chose A, which is greater than on the top, right? What happens is the velocity on the top is greater than the velocity on the bottom. The velocity above is greater, so the pressure is less. Pressure is higher under, keeps the airfoil up. Right? So A is the correct one. If you choose B, your airplane crashes. Okay, let's do another one. Oops. What is total pressure? is the sum of static pressure, dynamic pressure, and one of those four. So 5, 4, 3, 2, 1, 0. All right, so total pressure is essentially all the terms in the Bernoulli equation. Right? So they're giving you two of the three, static pressure and dynamic pressure. Which one is missing? Wow, look at that. Which one is missing? Almost a tie between A and B. They're both wrong. They're both wrong. Which one is the static pressure in the Bernoulli equation? P, right? And which one is the dynamic pressure? The 1/2 rho v squared. So what is missing is the G, the term that has G in it, which of course is hydrostatic. So this just shows you how much more you need to read before you come to class. And maybe we'll do one more. So here you see a streamline pattern for water. It tells you that it's water. So it's a streamline pattern in a flow field. It's a steady flow of water. Which statement best describes the normal and streamwise accelerations? Okay, so 5, 4, 3, 2, 1, 0. And finally, the majority gets it right. But there is both streamwise and normal to the streamline's acceleration. How do I know that? Well, how do I know there is a streamwise acceleration?
The flow rate M stay the same, so the velocity depth will increase.
Yeah, we see that the flow is narrowing down, right? So, and we know it's steady. They tell us it's steady. So for the same mass flow rate to go through two sections of this flow, it has to speed up as it narrows down. So there has to be a streamwise acceleration. And how do we know that there is a normal to the streamline acceleration?
Curvature.
Because the streamlines are curved. The streamlines are not straight. They're curving as they go in. So the only way a path of a particle can bend is there is a normal acceleration to the streamline. Okay, so we'll leave that there. Anybody has any questions about these 4 or so questions? Okay, so in fact, let's talk a little bit. All these issues will come up as we look at some of the equations today. But at the end of, or sometime during last lecture, I showed you a video of flow measuring devices. And I want to talk a little bit more about them. We already saw the pitot tube and how it works. But then we saw the video of the Venturi orifice, or they also call orifice plate, and then the Venturi tube. And we haven't seen how those work or how you can determine what they do based on the Bernoulli equation. So, but before I do that, and in connection, in fact, with one of the questions that we saw, a while back we talked about the force equation, Newton's second law, normal to the streamline. Remember first that when you apply Newton's second law along the streamline, the way we did it in class, that's how we arrive at the Bernoulli equation. But we also talked a little bit about what happens when you apply Newton's second law across streamlines. And that was the schematic, in fact, that I used at the time. So I have a streamline there in blue. And I am trying to see what happens when I apply my equation for the second law of Newton to that streamline when I applied normal to it. So I want to apply in the direction of n, which is perpendicular to the streamline. And just like before, we have gravity pointing down, just for convenience. And then the angle that the normal makes with the vertical is what we call theta. So that's the same drawing that we did before. And this is the equation, in fact, that we arrived at when we did that. So we just took our equation that has the gradient of pressure, the gravitational term, and then the acceleration on the right-hand side remember, it comes from F equals MA. And we wrote it normal to the streamline, and we came up with that. And just to remind your memory, this last term is the acceleration, but it's because we're normal to the streamline, what we see is that acceleration that is always pointing towards the center of a radius of curvature, which is this capital R that you see there. So that's just the so-called centripetal acceleration. And then we have also written the component of the gravitational force in the direction normal. That's why there is a cosine there. So one thing that we can do is, if we look at that triangle that is formed between n and the vertical direction, we can find that the cosine of theta could be written as dz over dn. Just looking at the little right triangle there. Just so that we can write this cosine in terms of the normal, like we have the pressure term. So if we do that, then we will replace that here. Now, just for the time being, to make our life a little easier, let's say that we're looking at some streamlines that are almost straight, or either straight or nearly straight. They're almost rectilinear. So what happens in that case with this equation? No, I'm not saying that the normal is going to be vertical. I'm saying that the streamline, you see it in blue, is not curved, but it's nearly straight. All right? It can be at an angle, but what happens if my streamline, instead of being bent like this, is nearly rectilinear? What happens? Let me ask somebody here. What happens in that case? Which term? No, the first term doesn't go to 0.
Rho v squared over r equals 0.
Rho v squared over r equals?
0.
Why?
Because r goes to infinity.
R goes to infinity. So if you have the limit of a curve, if you make it straight, the radius of curvature is infinity. So the term that goes to 0 is actually this one, if I make that assumption that my streamlines are almost straight. So they would look like this sketch down here. Now they're almost rectilinear. They're still at an angle, but under that assumption I can eliminate the acceleration term, and therefore all I have is, if I knock out that term, right, all I have is this equation, minus dp dn minus rho g dn dz dn equals 0, which is starting to look a lot like what? Chapter 2.
Starting to look at the pressure formula
For what situation?
for just like any depth.
Hydrostatics,
Hydrostatics.
right? It's starting to look a lot like hydrostatics, right? Because now the velocity is gone, right? The acceleration is gone. This is just a force balance. So if I take that and I integrate it, across a couple of streamlines. So let's go back to this, leave this picture here. All right, whoops, you didn't see that. Take a couple of those streamlines on top, and I'm now going to integrate this equation across two streamlines. So if I just do a straightforward integration, and I assume that, that the density is constant, so I can integrate the second term without having to worry about the integral involving rho. So of course the integral becomes just a delta P minus rho G delta Z equals 0, which again is looking more and more like a hydrostatic equation for the pressure at a certain depth. So I can also write that, of course, as P2 minus P1 equals rho G Z1 minus Z2. I just move one term to the other side of the equation, but this is a straight manipulation. So here's the two streamlines that I integrated, say, from 1 to 2, and I get that the difference in pressure between those 2 points, P2 minus P1, is just rho G Z1 minus Z2, and I can call, for example, Z2 minus Z1, call it H, and then you indeed have what we just said. This is just like a hydrostatic result. So see how we went from the general equation for a curved streamline using a force balance, making the assumption that the density is constant just like we did for the Bernoulli equation. And then by also assuming that those streamlines are almost rectilinear, they don't really have a bend to them, then we get this result, which is pure hydrostatics. So I can go, as long as I go normal to the streamlines, I can use this equation to find a pressure difference between 2 points. So that's the second tool for us. So we have the Bernoulli equation, which we know we can only apply along a streamline. And then we have this equation if we want to go perpendicular to the streamlines. And this becomes useful in many problems in which you need to find the pressure difference across the streamlines as opposed to along the streamlines. It happens a lot when you're, in fact, looking, for example, at measuring devices. We'll see that in an example. Any questions? Oh, yes?
Should it be Z2 minus Z1 on the last term or parentheses?
Here?
Yes.
No, because unless I made a mistake, I moved the term to the other side. So if I switch these two signs, they're both positive, then this is P2 minus P1, and this would be Z2 minus Z1, but I put it on the other side. So it's just a simple manipulation by moving terms around. So otherwise, plus another reason we know it's right, because otherwise I wouldn't get this, which we know is hydrostatic. The pressure at 1 should be larger than 2 if indeed 1 is below 2. All right. Okay, any other questions? Okay, so let's take a look at a measuring device such as a Venturi tube. We saw a device like this in the video last week. Let me make this a little smaller. That's a Venturi meter. It's just a device that uses Bernoulli's equation to determine the flow rate through a pipe. And in fact, any of these devices work the same way by changing the diameter through which the flow is going, whether it is just a plate that has an orifice, as you saw in the first part of the video, or whether it is something more elongated like you see here, which is more like a Venturi tube. So here's my pipe. Say the diameter of my pipe is capital D. The contraction has a different diameter, and we call that lowercase d. So that's the narrowest point across that Venturi device. What I'm interested in is in the flow rate Q. And what I can do is I can measure, by using a manometer, I can measure the pressure difference between those 2 points, between 1 and 2. So if I manage to measure the pressure variation between 1 and 2, I can use the Bernoulli equation to find the flow rate. And that's very straightforward, really. So you go ahead and write your Bernoulli equation. between points 1 and 2. I put all the terms first, and then I eliminate the ones that I can get rid of. So the first one I'm getting rid of is, of course, the rho GZ1 and the rho GZ2, because if this Venturi meter is level horizontally, then the height is the same for 1 and 2, and that goes away. So right there, I have an equation then, if I solve for one of the velocities, so if I take that and solve for, say, V1 square, by manipulating the equation a little bit, then I have a connection between V1 and V2. And of course, the connection is through the pressure difference, because that's the only terms that are left in the Bernoulli equation. So that's why I'm saying if we manage to measure P1 and P2, or their difference rather, then we could find the velocity. We do have a problem here, of course, which is that we don't know either V1 or V2. So what could we do? How about lady right there? I don't know V1 or V2, so this equation has two unknowns in it. What can I do to move forward? No, even if I find the pressure difference, I still have two unknowns. Back there.
Is that the equation, A1 V1 equals A2 V2?
Yes, there is. What is that equation? Conservation of mass. Last lecture also. So I know from conservation of mass that the product of rho, V, and A must be constant, because that's mass conservation through the across two different cross sections from last time. So of course I eliminate the density, because it's the same. This is Bernoulli's equation, assuming that the density is constant. So what he say, V1 A1 equals V2 A2, but I'm just writing A1 and A2 in terms of the diameters. So of course they appear squares. And that is the second equation that I need. Because as long as I know the geometry of my device, I know the diameters capital D and lowercase d, now I have two equations and two unknowns. So I am good to go. Take those two equations in the red boxes and together solve them to get, say, V1. So combine them, crunch, move things around, and you find that V1 is the square root. The square root always appears typically because, of course, you have a V1 squared. So when you write it in terms of the pressure, there's always a square root. So the square root of 2 times the pressure difference divided by the density of the fluid, and then further divided the whole thing by the ratio of the diameters to the 4th power minus 1. And now I know everything. So as long as I measure, of course, the pressure difference. If I measure the pressure difference, then I can put it in there, and I have an equation then for the flow rate. And that's essentially how flow measuring devices work. And this would be exactly the same whether it's a Venturi tube like that or whether it's an orifice. As long as you have the measurement at the two proper locations of the pressure difference, then you can get the flow rate. It's really not that complicated. I mean, at least the theory behind it is very straightforward. Does anybody have a question? Okay. Let's see some other applications of the Bernoulli equation. Oh, by the way, you might wonder, what about that material about the variation across the streamlines? If I, for example, had a very simple manometer here, which could just be two tubes sticking up, as long as if I make them long enough that the fluid doesn't spill out, I could just have two little tubes attached to the pipe and sticking up, and the fluid rises in those tubes, depending on whatever pressure it has. Then, yes, as I go, say, for example, from the center line of the tube up to the upper level, where it's open to the atmosphere, I will have to know what that pressure variation is say from 1 to the top of the tube. And essentially what I am doing in that case is I'm crossing streamlines perpendicularly to them. So if I cross from 1 to get up here somewhere, at least while I am inside the pipe, I'm crossing streamlines in the direction normal to them. So I could find that pressure variation, say for example, between 1 and outside atmospheric pressure by simply knowing the height of that column, because it's like a hydrostatic calculation like we just saw. Okay, let me show you another example of the use of the Bernoulli equation. We can use it to find, for example, the flow rate in what we call a free jet. A free jet is nothing but a jet of liquid, for example, that comes out of a hole of a pipe. For example, if you have a tank that is emptying through this opening here. Again, this is a straightforward application of the Bernoulli equation. What you always have to remember is that you have to follow a streamline if I want to apply the Bernoulli equation. So I kind of drew a streamline there, because if you were to look at the velocity field, let me sketch that here. If somebody asked me to draw a crude sketch of what the streamlines in this problem might look like, I might say that if this is the tank, if I make a crude reproduction here of that drawing, and here is the free surface. If I pick up any point here on the surface, it will probably have to do something like that. If I just draw velocity vectors and then I draw the tangent to all the velocity vectors, it would be something like that. I could do several of them. They would all tend to converge towards this opening. So those would be more or less what the streamlines would look like. So I just picked one, and it's right there on top. And but then I say, okay, I'm going to use Bernoulli's equation. Is there any requirement of the Bernoulli equation that I might violate with this problem? Density is the same. This is liquid water. So that's not a problem. What else?
You're neglecting shear forces?
I am neglecting shear forces, and we're going to have to live with that for now. And remember, I told you that that's okay if you're away from walls, for example. And notice that I pick a streamline that is more or less in the center of the tank. So it's away from the side walls. And I'm following it kind of through the middle of the pipe. So I don't want to be really close to the walls, because I know that I am neglecting shear forces. Okay, so that's one. Anything else so we have, somebody said constant density, shear forces. Anything else?
Steady flow.
Steady flow. Could that be a problem here? Why? Remember the definition of steady flow is what? That if I look at the flow field now, and I look at it a little later, it looks exactly the same. Clearly that's not going to happen here because that level is dropping. So if I take a picture now and I take another picture 10 seconds later, it might very well be that all the water is gone. Right? So we have a problem of unsteadiness in this flow unless what? I could keep feeding water to the top. What if I don't? That could be a solution.
The diameters could be largely different.
Yeah, if the diameters are largely different, so this diameter little d is a lot less than the diameter of this tank, then the level is going to drop very slowly. And if the level drops very slowly, I can make the assumption that it is maybe not steady, but quasi-steady. Remember that word from thermal. So it's quasi-steady, and that's good enough. It's an approximation, but we can live with it. So either because I continue to refill the tank, or because I make the diameters very different, I can assume that the flow is steady. So suppose that we do that. So steady flow, H changes very slowly. H, remember, is the height of to the free surface in the tank. So if I make those assumptions, Then here's everything else that we listed, no viscous effects. Then I'd write the equation again, write Bernoulli equation between points 1 and 2. Move this down a little. Same equation as before, same Bernoulli equation. You'll get tired of writing the same equation over and over. So, and then it comes to seeing what we can throw away in this equation. So what do you think we can throw away? P1Y. Huh? Oh, V1? Why? There's always a Y, no matter what you say. Because what we just said, right, is that the level is dropping very slowly. I will get away by neglecting V1. What is P1? It's atmospheric pressure. I mean, it looks like this is open to the atmosphere. What about P2? This is sometimes a source of confusion. What's P2? Out here in the jet, where the water is out already. Huh? It is atmospheric pressure, to a very good approximation. That's why I put 2 out in the jet, where it's not, I mean, you could make it very close to the outlet and it would probably still be the same, as long as you just pass the outlet. So indeed, P2 is also atmospheric pressure. Because every time you have a jet that issues into the atmosphere, the pressure in the fluid in the jet is pretty much atmospheric pressure. There are tiny variations due to the fluid mechanics, but the thermodynamic pressure, which is what we want there for the static pressure, is pretty much atmospheric pressure. So P1 and P2 are the same. I can knock them out. Right, and you just said the condition about V1 being very small. The last thing that I need to do is to pick a reference level. And for convenience, we can put the reference level at 2, so that we measure vertical distance from there. That way, Z1 is 0 and Z2 is 0 and Z1 is just H. And that really finishes the problem, because if I substitute all those things in there, I really only have 2 terms left. The rho GH and the rho V square, V2 squared over 2. That's all. So you can solve for V2, and there you have again the square root. It's just a lot simpler than in the previous problem, than in the measuring device. It's just the square root of 2GH, which rings familiar, right? If I drop this pen and I neglect the friction with the air, what's the velocity when it touches the floor? Square root of 2GH. That's what it is, right? Because in fact it's the same principle. Right? So the water is essentially like it's falling from 1 to 2. Right? The fact that it turns doesn't matter too much. So, all right, so that's a free jet. Any questions? Now, there is something else about these free jets, and it is that in fact, when the jet issues from an orifice, it is normally not the same diameter as the orifice. You can do this experiment very easily at home. What diameter does the jet have compared to the diameter of an orifice? So, you know, take that or something larger, maybe so the velocity, so the H is a little bigger, and then puncture a hole. And you see this jet coming out. What is the diameter of your jet compared to the diameter of the hole? Have you seen that? You haven't done that? Haven't had the curiosity of punching a hole? For example, take a plastic soda can, fill it up, and then puncture a hole in the bottom. Kind of see the hole and then see the jet. It's always smaller. So it actually kind of looks like this. It's called a vena contracta. So there is the diameter of the hole is capital D. The jet itself is lowercase d. which is smaller. All right? Do it. You can try to kind of see it just by eye if you do this. And why is that? Imagine the opposite scenario where the opposite scenario would be if I repeat the drawing here. Right, that the jet issues exactly the same diameter as T. Can you think of the physics of these two scenarios and then maybe conclude that the second one is not really possible? Huh? Yeah, that's along the right explanation. What about the streamlines? They don't want to. They have their own personality. They don't want to change. They don't want to take a sharp turn.
Isn't there also gradient pressure taking into account because like it's faster velocity or something?
No, he's close to the answer. The streamlines don't want to take a sharp turn.
Is it because of the no slip condition?
No, obviously I have to have no slip. So, you know, really, if I'm looking at the very infinitesimal layer of fluid that is attached to the wall, that actually is not moving. But you just have to look at a streamline a little bit farther away so that actually it can flow. So let me draw it here. Suppose that I am following a streamline somewhere here. It still has to make a very sharp turn, which is what he's saying. He's saying the streamline doesn't want to take a sharp turn. What does it imply if something takes a sharp turn?
That your acceleration is getting larger and larger.
In fact, if it's completely sharp, it's infinite. Like if you're going in that direction and all of a sudden you're going in that direction, you either got hit, got a very, very big whack that made you, and even then it would be impossible because the acceleration would be infinity. So the fluid cannot really make a 90-degree turn. It really does a more regulated turn. Even if there is a large acceleration, that acceleration cannot be infinity. So this is what happens, that you have that constriction, and then we define something that is called the contraction coefficient, which is the area of the jet divided by the area of the orifice. And that's always a number that is less than 1. And so people do measurements carefully or do numerical simulations to find out what the contraction coefficients are. And then you end up with, let me put this right here, with things like this. This is in your book. For different types of openings, you can actually measure the diameters or compute them if you do a very careful numerical simulation, and you get contraction coefficients. They're always less than 1. And you have here 4 different situations that you can find that are in your text. All right? That's something that you have to take into account when you do this type of a problem. Okay, let me see. We still got some time. Maybe I'll skip this one. Here's another situation that is good for you to know. Suppose I have this problem. Let's see. Here's the problem. Another tank. This time there is an orifice at the bottom of the tank. But the tank contains 3 different fluids. Water at the bottom, so heavier is at the bottom, medium weight is in the middle, the lightest is on top, which is the air. And we can, for example, pressurize the air on top. So if we close it and we pressurize it, we can measure that pressure. And let's say that the pressure there in the air is measured by that gauge and is P naught. And I can also measure the thicknesses of each of the layers for each fluid. And then all I want to know is find the initial flow rate. So if this is initially closed, for example, and I just open it, and the water starts flowing out, I just want to determine what the initial flow rate is. So I don't really want to worry about the same problem that we had before of the level dropping. Let's just find out initially, how many cubic meters of water per second or per minute, depending on the size, are coming out. All right, so again, this is an application of Bernoulli's equation, but you have to be very careful. Why do we have to be very careful? Because I could do the same thing. I could say, let's draw a streamline. And indeed, I could say, here is the tank. I could say, well, start from the top and go here to the bottom. So that dashed line is my streamline. What's the problem with that? The density is changing. Right? So you cannot apply Bernoulli's equation directly to a situation where the density is changing, because the Bernoulli equation that we derived requires that the density be constant. And we're going through 3 different densities here. So what do? Well, we take note of that fact that the density is not constant between 1 and 3. So there is my hypothetical streamline from 1 to 3. So what I do is I have to break down the problem in parts. I know, for example, that I can apply Bernoulli's equation from 2 to 3, because that's the same fluid. That's through the water, from 2 to 3. What I cannot do is apply from 1 to 3 unless I'm very, very careful. So it's best to split it into 2 parts and essentially apply Bernoulli's equation from 2 to 3. Right? But between 1 and 2, recognize the fact that, again, they're telling us that let me shrink it a little bit, that the ratio of the areas is very small. The area of the orifice is very small compared to the area of the tank. So that the velocity of those levels is very small. The blue level and the orange level is dropping slowly. So if I go then from 1 to 2, all I have is a hydrostatic situation. And that's written here. The pressure at 2, which is only going through the gasoline, right? At 2, this is the gasoline, this is the air, and this is the water. So if I'm just going through the gasoline, all I have is a hydrostatic situation, very low velocities at 1 and 2, and therefore P2 is equal to P1 plus the column of gasoline, the thickness of the gasoline, times its specific gravity. Make the note V1 is almost 0, just like V2. And then you go ahead and apply the Bernoulli equation between 2 and 3. That's not a problem. Again, eliminate the velocity at 2 because it's low. Wide area at 2. And you could take that equation and solve for, this is V0, the velocity through the orifice, just by solving the Bernoulli equation. So you have a pressure variation between 2 and 1, and you have between 3 and 2, and then you have a hydrostatic term. So you put that in there. And solve. Again, to save time, I'm not going to go through all the steps, but I'll show them to you. So if I solve, and substitute, right? So P2 is P0 plus atmospheric pressure plus the gasoline weight, and then just plug that into the equation. And eventually, after you go through all the steps, you can write it this way. This is what you get out of the Bernoulli equation between 2 and 3, but after you substitute in what you got for the hydrostatic effect of the gasoline. So you have that the term density of water V naught squared over 2 is just the pressure, the gauge pressure that you're measuring, plus density of water, gravity, thickness of, gasoline, density of gasoline, gravity, thickness of the gasoline layer, plus density of the water, gravity, thickness of the water. So you can see how this is like a modified Bernoulli equation because we went through two different fluids. And essentially what it is, these two terms that I underline here are essentially the hydrostatic terms of the gasoline layer and then the water layer that sit above the orifice. So once you figure that one out, then you could do it without going through all the steps because you know you're adding the hydrostatic effects separately. Let's see. Okay, 5 minutes. Let me show you. Is there a question, quick question that we can answer maybe? Let me show you a quick video. Have you heard about a phenomenon called cavitation? Cavitation. Anybody? What's cavitation?
It's when like the fluid kind of forms a bubble or something.
It doesn't have to be a big bubble like that. It could be a tiny microscopic bubble. But yeah, it is the formation of a bubble. Essentially, again, think of Bernoulli equation. By now, I expect you all know that if the velocity goes up, what happens to the pressure?
Down.
Goes down, right? What happens if the pressure goes down too much? It might reach the vapor pressure. Remember thermodynamics? If I have a liquid and I start dropping the pressure, I might reach the pressure. Remember the saturation pressure? I might reach the saturation pressure at which that liquid changes phase at whatever temperature I have. So I'm dropping the pressure. I reach the saturation pressure. He said a bubble forms. It could be a tiny bubble initially. It could grow. If it grows and it's just vapor, then we speak of flashing. But if it's cavitation, those bubbles that form all of a sudden can collapse. And let me show you what happens. So you just took like a 1 minute portion of this video.
Does that generate any heat if it did that?
I'm sorry?
Does that generate heat? Or like how
No, it doesn't generate heat. Oh, here it is. Okay, so look at this. But it generates something else that is worse.
Metal erosion is a costly problem. It attacks pumps, valves, piping, and other expensive equipment. No matter what type of liquid is being used, there's always a risk of damage from flashing and cavitation. Wherever there's a restriction in flow, the decrease in pressure can cause a fluid to reach its vapor point. Flashing occurs when the fluid vaporizes and remains a vapor. Metal erosion caused by flashing appears smooth and shiny. Cavitation occurs when the fluid vaporizes, then returns to a liquid state as the pressure increases downline. The metal damage caused by cavitation is rough and irregular due to pitting of the surface. Cavitation is a major source of damage in control valves and other components. Cavitation occurs as a liquid passes through a restriction, such as a valve. The restriction causes the liquid's velocity to increase and its pressure to decrease. The point of maximum velocity and minimum pressure is called the vena contracta. Vapor bubbles form in the liquid when the pressure falls to near the level of the liquid's vapor pressure. When the pressure recovers downstream, the vapor bubbles implode and return to liquid form. After the initial bubble formation and collapse, the bubble may reform and collapse a second time. Liquid microjets form when the recovering pressure makes an indentation in a bubble. Then the microjet bursts through the bubble. These implosions can also cause local pressure waves of up to 100,000 pounds per square inch. The combination of pressure waves and microjets can cause severe damage to the valve plug, seat, and body when they're located near the vagina.
So you heard that, 100,000 psi of pressure. When those microbubbles explode again, there is a huge pressure increase and it damages the equipment. It can happen inside a valve, it can happen in a propeller that is spinning fast and is high velocity, low pressure, anything where the pressure might drop. And this is a very serious problem. All right, so we'll meet again on Wednesday.